When will the sun make the earth uninhabitable? How many? 4.5 billion years. That will be about the time the sun will start to convert to a red giant. But we're looking at a much sooner disaster when the sun gradually heats up. The sun is about 20% hotter now than when it formed, and it's continuing this progress of warming up. And the cause of that is the growth of the helium nugget in its core. As it fuses hydrogen into helium, that helium just falls to the center, and it grows into this inert core, which takes up space, and that impedes the fusion reaction going on. And to compensate for that, the sun has to warm up. So probably in about 200 million years, it will be too hot here. And then the oceans will evaporate or boil away, and life here will be impossible. What should we do about this? 200 million years is probably enough time for our politicians to make decisions. So what should we do? Yeah, being optimistic. Yeah. So what should we do about this problem that the sun is going to overheat the earth? Got a bunch of rocket scientists in the room. We probably ought to be able to solve this problem pretty quickly.
Move to Europa.
Move to Europa. Okay, now taking the current population of the Earth to Europa is probably not feasible, although we could seed Europa with perhaps a contingent of humans. And by the way, Mars wouldn't be a bad choice either. Mars has a few extra 100 million years before it gets too hot there. But how do you save the Earth from this onslaught of solar radiation that is looming before us? We could move the Earth, and many people have tried, but how do you move the Earth? Oh, now you want to do the pragmatic solution. You want to put a sunscreen up. Instead of moving the Earth, what if we block some solar radiation? Which we could do. Put up a bunch of mirrors at, what is it, L1, which is between the sun and the Earth? Nice gravitationally stable point at L1. Just 100,000 mirrors that we could rotate in and out, control the weather here, control the amount of solar radiation. If we were worried about the Earth being too warm, well, we have a solution at hand. On the other hand, that's not what we're supposed to be talking about. I am here today to talk to you about clean code. Before I do that, let me give you a little bit of history. How many programmers are there in the world today? Even if you don't count the VBA programmers, how many are there in the world today? 100,000. Oh, heavens. There's 100,000 in this city. I'd say 100 million, 200 million, something on that order. Not yet a billion. It's not 1/7 of the population, but probably it is 1 to 2% of the population of the planet is a programmer. Consider that. That's a very interesting number. 100 million, 200 million, 300 million programmers in the world. How many programmers were there in 1946? 70 years ago. There were some. There was one at least. Alan Turing wrote some code back on the very first computer, the automated computing engine back in England in 1945, actually. And he wrote in machine language, didn't even have an assembler, base 32 he was using in those days. Wrote some floating point packages, invented the concept of the stack. Nobody even thought about a stack before then. How did we get from 1, 70 years ago, to hundreds of millions today? What kind of growth curve is this? It's got to be exponential. There's no other way to do it. And exponential curves have a doubling rate. And you can work out the doubling rate. 1 to 100 million over 70 years. Gee, that's a doubling every 2.5 years. Now, I don't believe the rate of programmers has doubled every 2.5 years, because I think in the first 10 years, the doubling rate was much shorter. But then after that, the last 60 years, it's probably been a doubling roughly around every 5 years. Every 5 years, the number of programmers in the world doubles. which means that our industry, our particular profession, doubles every 5 years. Half the programmers in the world have less than 5 years experience. And this is always true as long as we're on this doubling curve, which leaves our industry in a state of perpetual inexperience. People look around and they say, well, you know, this programming thing, this must be a young person's game because there's hardly any old people. Where'd all the old people go? We're all still here, most of us in this room. There just never were very many of us to begin with. This is the essential problem that we have with our industry. Our industry is dominated by this influx of very inexperienced people who have sometimes gone to degree programs or sometimes not, and who believe they understand what software is and never have the time to accumulate the experience and have no sufficient mentors available because there aren't enough of us. And so we wind up with this perpetually inexperienced group of programmers. And the problem with that, of course, is that programmers rule the world. Nowadays, nothing happens in our society unless it's controlled by software. Pretty soon, you won't even be able to drive a car. Even now, you think you are driving the car. Has anybody had to drive one of those cars that will automatically put the brakes on for you? If it sees, you know, it's got front-looking radar, how cool is this, you know, and you get too close to a car and it automatically hits the brakes. Has anybody had it falsely hit the brakes when there's nothing wrong? There's just some truck off to the side and it managed to encroach on the radar beam and the car panics, sets off the alarm, smashes on the brakes, and you get rear-ended by somebody. That happened to me yesterday. I didn't get rear-ended, but the software in that car made a decision that I would not have made, and it overrode me. Now, I can turn that feature in the car off, and I am often tempted to turn that feature in the car off. On the other hand, I think there's probably a safety issue there where I want the car to panic more than I do, but I'm on the fence as to whether that's the right decision or not. Very little happens in our society without us, programmers. People interact with software systems on a minute-by-minute basis. Even people who have no idea what computers are, your grandmothers, if they're still alive, will interact with software systems on a minute-by-minute basis. You can't buy anything. You can't sell anything. No law gets written. No law gets enforced. No insurance policy is active. Nothing happens in our society unless it is mediated by software. We rule the world. Other people think they rule the world. Then they hand the rules to us, and we write the rules that execute in the machines that govern everything. One day, some terrible thing is going to happen. Some poor software guy is going to do some dumb thing and kill 10,000 people. And it's not hard to imagine what that would be. The events that might kill 10,000 people are pretty close to us. We know what they are. And when this happens, the politicians of the world will do what they must. They will rise up in righteous indignation, and they will point their fingers squarely at us, programmers. We've already seen what happens when the politicians point at executives. The CEO of VW in North America stood before Congress and testified. It was just some software developers who did it for whatever reason. That was a quote. We see what happens when the executives are pointed out. They just hand the blame off to us. And the blame will come to us because, in fact, it was a couple of software developers who wrote that code in the VW. For, well, probably not whatever reason, probably some reason. But those developers who wrote that code broke a rule. They violated a sacred trust. They made all of us look bad. And they made it credible for us to be blamed. This is the world that we are entering into. At some point, the politicians will have to regulate us. There will have to be rules about what languages we use and what frameworks we use and what practices we follow and what processes we follow, what signatures we have to get, what courses we have to take. All of this will become a matter of law because we have too much influence. We need to be regulated. I hope that we can get there first. Many other industries have done this. Doctors did this. They got there first. They laid their own rules out. And then when government did finally come around and say, hey, we need to regulate you, the doctor said, well, here's a bunch of rules that we've been following for a long time. And the government, being essentially lazy, said, that's great, we'll make them laws, and that's fine. Accountants did the same thing. Can't really count lawyers because they write the rules anyway, so we won't count them. But we need to get there first. We need to invent the rules. We need to define what our ethics are, what our professionalism is. We need to regulate ourselves before government gets there first. And I think the race is on, and I don't think we're winning it at the moment. So it's my little pitch. I started programming 1964. I was 12 years old. My mother bought for me a small little computer, plastic thing. It had 3 flip-flops and 6 AND gates, all mechanical. Little flip-flops were plastic. They slid back and forth on racks. They had 2 states, 0 and 1. You had AND gates, which were little metal rods that slipped into holes on those flip-flops, and you could block those rods by slipping little tubes onto pegs. Those rods were AND gates. And if the AND gates slipped into the rod, it slipped into the grooves in the flip-flop, they would actuate another rod which would change the state of the flip-flop. This was, in essence, a 3-bit finite state machine. And you could program it by putting those tubes on the pegs. And if you put the right program in, it would count. It would count from 0 up to 7. I learned binary this way. I learned octal that way. If you programmed it a different way, you could count down from 7 to 0. And there were many other programs you could put into it. There was a full adder, taking 3 bits and turning them into a sum and a carry. There was a number of other programs. I loved this machine, but I had no idea how it worked. I was 12 years old. I couldn't figure it out. At the back of the manual, the book with all the experiments in it, there was a paragraph that said, if you'd like the advanced programming manual, send in $1 and a self-addressed stamped envelope. Anybody remember that? And we will send you the advanced programming manual. Now, this was long before there was an Amazon, so it took 6 weeks. But 6 weeks later, in the mail, here's this little manual. I have it today. It's in a Ziploc bag. I keep it in a place of honor on a bookshelf. I opened it up not too long ago, and I read through it again. It's maybe 20 or 30 pages long, just a little pamphlet. The most cogent description of Boolean algebra I have seen written for a 12-year-old ever. It was completely unapologetic. It just started out with truth tables and Venn diagrams and Carnot maps and went right into Boolean variables, the associative principle, distributive principle, De Morgan's theorem, right through, bang, 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 bang. And then it said, okay, now you know how to manipulate Boolean equations. Here's how you program this machine. You write down the truth table, the state transition table for all those flip-flops. You convert them into Boolean equations and over or. You reduce those Boolean equations to lowest terms, and once you've got a nice little set of Boolean equations, here's how you put the tubes on the pegs. And a little mapping function from the equations to the tubes on the pegs. And I had a program in mind. It was called Mr. Patterson's Computerized Gate. I wrote down the truth table for the state transitions. I turned them into Boolean equations and over or. I reduced them to lowest terms. I put the tubes on the pegs. I cycled the machine with a little crank, and that machine did exactly what I wanted it to do. And I was a programmer. That was it. That changed my life. I became a programmer. I felt the power of controlling the machine. I imagine some of you had a similar experience. Maybe not with a plastic computer, but maybe you went to Radio Shack one day and wrote a little basic program that printed your name in an infinite loop, and you went, yes, the power. I'm a programmer. In 1977, I was working at a company. We were shipping measurement systems to telephone companies. And the device we shipped was an 8080 based machine. Anybody remember 8080s? 8-bit microprocessor. 64K address space, 32K of RAM, 32K of ROM. This thing went into a box. We bolted the box shut. We hauled it off to telephone central offices, bolted them into 19-inch racks, and walked away. Right? We had hundreds of these things scattered around the world. The software was written in assembly language, 8080 assembly language, one source file, 32K long. The code was a single program. We would compile it using an assembler on a VAX. We would then download this code into a prom burner, and we would burn the ROMs. 2708s they were. They were 1K by 8 read-only memories. You could erase them with ultraviolet light. Programmable and erasable. EPROMs, we called them. 32 EPROMs get burned. You have to plug them into boards. Each board could hold 12, so we had 3 boards. And you plug them into the boards. You have to make sure they're in the right order. Right, so we labeled every prom. And then you'd plug the 3 boards into the back plane, bolt the thing up, turn it on. It would work. We'd ship it out to all of our sites. What was the procedure for changing one line of code? If you wanted to change one line of code, what did we have to do? And the answer is, well, if you change one line of code, no matter what that line of code is, if you add a line or take away a line, all the addresses change. All the subroutine addresses change. So you've got no choice. You've got to reburn all 32 of those chips, redeploy them all, ship them all out to all of the field service agents out in the world. They have to drive all of those 32 chips hundreds of miles to each of the central offices, unbolt the box, take the boards out, pop all the old chips out, push all the old new chips in the right order, please. Of course, all the labels fall off the chips because they go through temperature changes. Anybody push chips into sockets?
Oh, sure.
You know how this goes, right? The little socket and like that, except sometimes it does this. And you can't see that. And so the guy would push the chips in, and sure enough, one of them would bend, and we'd have to ship him extra chips because you can't unbend the pins. They break off. So this was very expensive. My boss comes to me and says, we have to solve this problem. We need to make it so that when we ship these chips, when we make a change to the software, we can make a change in one chip and just ship that chip. Now, how do you do that? Well, we thought about this for a while, and we came up with a solution. It's not a very difficult solution, actually. C++ programmers in the room will recognize it. In order to be able to ship just one chip, what we did is we found every subroutine in this system. If a chip had 5 subroutines on it, then we created a table at the top of that chip. In the address space of that chip, there was a table which contained the pointers to the 5 subroutines within that chip. Every chip had this little vector table in it that we would load into the chips. Then at boot time, we would take all those vector tables and we would move them to RAM. So there was a dedicated area of RAM where all those function pointers were. And then we changed all the calls to the subroutines to calls through those RAM vectors. And all of a sudden, we could ship one chip. What had we invented, by the way, in 1977? Yeah, indirection. Well, certainly we had invented indirection, yes, because all problems can be solved with indirection. We invented vtables. We invented objects. This turned into a little object-oriented program. The little chips were independent objects that had polymorphic behavior. In fact, what we could do now that we had done this, and this was an unintended benefit, is that we could dial up our machines. They had modems in them. We could dial up, and then we could write patches by adding new functions or replacing old functions by writing the new function in RAM and then changing the RAM vector pointer. So we didn't anticipate that benefit, but it gave us the ability to override functions existing in ROM. Fascinating. Anyway. I want to talk to you today about a discipline. It's a discipline which I call clean code, and we're going to focus particularly on the issue of functions. And let me show you what happens when this goes wrong. I think I can do this. Let's see if I can plug this in here and get the sound correctly. Good. All right. And you can see that on your screen. The code you are about to see is real, although it has been obscured. It's Java. I do want sound here in the sound booth, unless maybe the sound's not working. Oh, yes, there you go. Thank you. Now you know what the Stargate actually was. It was somebody's bad code. This is 32,000 lines. It is a single Java class, not a single Java function, although it's hard to tell the difference here. It's actually two classes in Java that were stuck together. One of them was called order, the other was called order impl. It forms the heart of a shopping cart application. This code was given to me in 2008. The authors of it, I was teaching a class there, and the authors of it handed it to me on a thumb drive and said, would you take a look at this and comment on it? So I took it back to my hotel room that night, and I looked at it, and then I got myself a bottle of scotch, and I made this movie for them. And I played this movie for them the next day, and then I asked them the important question: how could you have let this happen? They'd been working on this for 7 years. I said, this is 7 years worth of work. How could this be 7 years of a team of, quote, professionals working together to create a software system? How could that be the output? And they gave me their answer, which is the standard answer: oh, we had deadlines. And I asked them, well, is this helping you go faster? Oh, no, it slows us down like crazy. Well, then how is this helping you go faster? How is this helping you meet deadlines? Oh, it doesn't help us, but it did once. It's worth just letting it play out. This is the sad story of all too many software teams in the world. They make a trade-off, and the trade-off is a poor trade-off. They believe they're going faster by making a mess. In fact, they're not. I have a rule, and that rule is real simple. The only way to go fast is to go well. If you want, and you know, it's kind of a grandmother rule. Your grandmother would tell you something like that. Son, the only way to go fast is to go well. Anything worth doing well. Anything worth doing is worth doing well. Blah, blah, blah. Okay. All of these rules, I think all of these moralist rules that our grandparents tell us apply to software pretty well. The only way to go fast is to go well. The only way to make deadlines, the only way to meet schedules is not to rush, but it is to be deliberate and disciplined and orderly and produce the best code that you can. And given that, I want to talk about functions. Now I'm going to show some code here. There it is. It's written in Java. Most of you, how many of you are C programmers? And how many of you are C++ programmers? And is anybody something else? Well, I mean, primarily, right? What are you doing? Who? Oh, Bash? Well, yes. Okay, is that what you primarily do? Bash scripts? Cool. Oh, so we got some Ruby on Rails guys in here? Ada. Ada. Really? Ada? Wow. Ada. Named for? Ada Lovelace. Of course, you all know that. Who was the daughter of? No. Lord Byron. Yeah, Lord Byron. Who was named the first programmer, kind of a misnomer. She did actually write some algorithms for the analytical engine, but never was able to execute them because there never was an analytical engine until the guys at the Smithsonian built one a few years ago. Why do we consider her the first programmer? Because primarily she was the first person, not just a lone woman, first person to recognize that a mechanical device that dealt with numbers could also take those numbers and use them to represent symbols. She wrote in the notes of her notebook that you could, instead of just calculating numeric values, you could have the numbers represent all kinds of interesting things. She was the first person to recognize that a computer was a symbol manipulator, not just a numeric manipulator. Who is the person who invented the word compiler? Who coined the term compiler? That was Grace Hopper. Grace Hopper was the first person to realize that a computer could be programmed in a language that was not one-to-one compatible with machine language. It was not an assembler, but could be something a little bit bigger than an assembler. And she actually wrote the very first compiler. It was called A0, the first version of the A compiler. Eventually, her work on that compiler and other compilers led to COBOL. Do we have any old COBOL programmers in the room? Yeah? And you survived. I survived too. I wrote COBOL for about a year and then managed to turn into an assembly language programmer, which was a much nicer language. So I'm going to put this code on the screen. It's in Java, but if you're a C programmer, you know Java, and if you're a C++ programmer, you know Java. And I'm going to give you 1 minute per screen. There are 3 screens, so this is going to take about 3 minutes. Actually, the last screen is a half a page, so 2.5 minutes. And at the end of that, I'm going to want you to tell me what this code does. And let's see, we're going to start that. These newfangled watches. Now I have to find the stopwatch. I think it's that one. I gotta wait for the stopwatch to boot. Reset, good, and start. What does that do? What did that code do? Okay, yeah, good. You spotted that one if statement that surrounded the whole thing. Yeah, if there's a test attribute set, then it surrounds some, well, let me take this. This is a wiki program. Probably you saw that it was a wiki. There's a wiki page. And in a wiki, the central concept of a wiki is the page. And this particular kind of wiki is a special wiki. It is a wiki that allows you to write high-level tests for large enterprise systems. Those tests are written on wiki pages. They're written in tabular format. You don't see that here, but they are. Like any test, you need to be able to set up a test, and the setup code would be on another page. And you also need to be able to tear down a test at the end. The teardown stuff is yet on another page. And this is the code that finds a page, and if that page is a test page, it surrounds that test code with the setup code and the teardown code, and then converts the whole thing to HTML. That's what this does. It's hard to see that in there. And the reason it's hard to see that in there is that this code is fundamentally rude. The author was rude. Now, I'm going to show you how to make this code polite. I'll show you what the polite thing to do. But let's examine the rudeness of this code. And the first little bit of rudeness is the name here. What is the name of this function, testable HTML? What does that tell you? And okay, first of all, it doesn't tell you much. It's a noun. Functions do things. They are not things. So this function should have some kind of verb name, not some kind of noun name. What the author has done here is he's named the function for what this function returns. Supposedly it returns testable HTML. Although that's not exactly correct, since it only returns testable HTML if the page is a test page. Otherwise, it returns non-testable HTML. So it is a fundamentally inaccurate name and probably ought to be changed to something else. There's a bunch of things here we can complain about, but I want to talk about something specific, which is this. There is no concept in this system more abstract, more high level than the wiki page. This is a wiki page, highest level concept in the system. So as you read this code, you are greeted with the highest level concept in the system. And any programmer would then breathe a sigh of relief and go, oh, good, I think I can understand this. It's the highest level abstraction in the system. The second line of code dives right down to one low-level thing called a string buffer. String buffer in Java is kind of like a character pointer in C or C++. It's an extremely low-level concept. So we have, in the space of 2 lines, the highest level concept in the system and one of the lowest level concepts of the system. This is rude. And it's rude because of how the reader has to respond to this. When you see something at a high level, you set the context in your mind. Ah, right, we're going to deal with high level concepts. And then the next line says, oh no, we're dealing with string buffers instead. So you have to take the high level concept that you just stuck in your brain and push it on your mental stack so that you can deal with the low level interrupt. And then of course what happens is that in the next line we have kind of a mid-level thing. Oh, page data.has attribute test. Well, this is not low level, it's not high level, it's in the middle. So now you're not done with the low level thing yet, but you got to remember it, so that has to get pushed on your stack as you now deal with this next mid-level concept. Now, the problem with this, as we all know, is that we don't have a mental stack. Human beings do not have stack pointers in their brains. We are not good at dealing with interruptions. Even at one level, we're not good at dealing with interruptions. And here's this code coming along and continuously interrupting our chain of thought. Now, how did it get written that way? Well, this is the way you write code. You write code by going up and down the abstraction levels all the time. Because you say, okay, I'm going to be dealing with wiki pages. Right, okay, all right, now, I'm going to need a string buffer. Right, okay, fine, all right. Is it a test page? Okay, it's a test page. This is the way you write code. It's not the way you read code. When you read code, what you'd like is for the interruptions to go away. We don't want to be going up and down the abstraction levels over and over again. A good rule of thumb for a function is that every line in that function stays at the same level of abstraction. Every line in a function stays at the same level of abstraction, and that level is one below the name of the function. So the name of the function is the highest level concept in that function. Every line is just one level below that, none of this bouncing in and out. Just to show you how bad the bouncing in and out is, we go into this test check here, then, if we're going to include a setup page, a really high-level concept here, wiki page, okay, page crawler. Well, that's got to be pretty important right there. And then there's a null check. Is that null check important? Probably it is, but it's a really low-level concept. And, now a wiki page path, that's really high-level. And path page name, that's kind of mid-level. And then there's a dot. Is that dot important? Do I have to understand that dot? Do I have to understand that line end right there? Is that important to the functioning of this function? Is that line end important? The poor reader is at sea. There's no way for the guy reading this code to assemble all these concepts into a single cogent framework in his mind without going over it and over it and over it and dealing with the fact that he doesn't have a mental stack, so he's got to rebuild all these mental contexts over and over again. This is just rude. The author was not thinking about you. The author was thinking about himself. And since I was the author, I can say that. Many, many years ago, fortunately. But let's continue, and I want you to look here at a pattern that evolves. And the pattern is fairly straightforward. We've got a null check, and then some page crawler stuff, and then 3 appends. Null check, page crawler junk, 3 appends. And then as we've paged down here, we will see, heavens, there's another null check, page crawler stuff, 3 appends. And null check, page crawler stuff, 4 appends. Ooh. There's 4 of them there. A preceding line end. Is that preceding line end important? Goes page down a little bit more. Null check, page crawler stuff, 3 appends. Now, very likely, the author of this code invented a little algorithm that had a null check and page crawler stuff and some appends, and he got that one part written and thought, I bet I could use that again, and he did a little copy-paste trick, and he pasted it 3 more times, and then he fiddled it into working, just adjusted it into working. Probably that's what happened here. That's rude. A good programmer would identify the fact that this algorithm is in there 4 times and pull out a function, extract a function. Give it a nice name, and then call that function 4 times with appropriate arguments. That's what a good programmer would do. A bad programmer would leave it in there like that, which would be rude. So I saw this code about probably about 7 years ago. I saw it. It was on my screen. It had gotten written 12 years ago, probably more like 15 years ago, actually. And I saw it, and I thought, well, this is a mess. I should clean it. So I cleaned it down to this level. This is just a straight refactoring, and you can see how the refactoring was done. I invented some functions called include setup pages, include teardown pages. Those are whole new functions that simply extracted all that code out into brand new functions. I changed the name of the function to render page with setups and teardowns. That's a nice verb. Tells us a little bit better what this function is doing. It takes a page and it puts the setups and teardowns around it. I suppose I could use a better name like render test page with setups and teardowns. And as you read through this, it's not hard to see what's going on, although there's still a lot of code here. It's not too hard to see what's going on. The surrounding if statement is clearly obvious. And I used a little trick here. This is called a descriptive variable or an explanatory variable. The only purpose of this variable here is to make this if statement read like a sentence. If is test page. Rather than putting all this gunk here into the if statement predicate, I can get the if statement to read nicely. And that helps people understand the intent. And then if it's a test page, well, then I get the contents of the test page. Oh, I've got this string buffer thing here still. I include the setups. I append the content. I include the teardowns. I put that content back in the page and generate HTML. The amount of time it takes to understand this function is dramatically less than the amount of time it took to understand the original function, although you don't understand it in as much detail. Now, that's actually a good thing. I don't want to understand it in as much detail yet. I may need to understand that detail at some point, but it might be that all I really care to know is that, oh, yeah, okay, if it's a test page, it's surrounding it with setups and teardowns. Okay, I get it. This allows me to bail out early. It's polite. It allows me to escape without understanding all the details. That first code that I had stuck up there, before you could understand what that did, you had to understand the dots and the line ends and the null checks. You had to understand all the details. It was rude. I would have to spend 30 minutes going over that code to understand what it actually did. This code here tells me at a much higher level, oh, okay, I know what this does, and I can get out early. It maybe take me 5 minutes to understand this. And if I didn't need to understand the detail, then I was done. This is an old trick used by journalists. Anybody ever take a journalism course? Or write a paper? Sure. Yeah. So what are the rules for writing a paper? First thing in the paper is the title. And the title should tell you roughly what the paper's about. And then after the byline, there's a paragraph. That paragraph is called the synopsis or the abstract or something like that. And in that single paragraph, usually it's one paragraph. Some people break the rules and make it two. In that single synopsis paragraph, you describe everything in the paper at extremely high level. And then every paragraph thereafter descends one notch down the abstraction level. Every paragraph it starts out very high level, and then as you move down the paper, it gets lower level and lower level and lower level and lower level till you finally get to the conclusions. And journalists follow this rule, and anybody writing a paper follows this rule because it's polite. It's a polite way to write a paper. It offers the reader the ability to exit early. How do you read a newspaper or a magazine? You scan the paper or the magazine for a headline that interests you. If the headline grabs your attention, then you read the first paragraph. If that grabs your attention, you read the next paragraph. And that is the algorithm. As long as you're not bored, you keep reading. As soon as you get bored, you leave. That's polite. Our code should have the same attribute. It should allow the reader early exits so that as soon as the reader gets bored, I'm done. I've gotten what I need. This gets close to that, not quite enough, I think, but close. You can see that most of these lines of code are roughly at the same level of abstraction, with maybe the notable exception of this string buffer stuff. But most of this stays relatively high level and just one level below the name of the function. And this leads us to a conclusion. If the lines of code in a function must all reside at the same level of abstraction, what does this imply for the size of the function? How big could a function be if all of its lines of code have to stay at the same level of abstraction? How big should a function be? What is the appropriate size for a function? What's that? So you can see the whole thing.
Yeah, you can easily understand all the concepts in the function.
Anybody remember these? That's a VT100. I have a VT100 emulator on my laptop. And it works too. I've got it set to 9.6, which was about the speed that these things ran at. Notice the curvature of the screen here, and you can see the video circuitry is a little bit old. It's dithering here. If you look carefully, you'll see there's a little bit of flag waving. Right? And if you look very closely, you will see an image of my face in the glass. Can't quite see it on the projector. I can barely see it on my screen. This is the rule. This is the screen that the rule was invented for. A function should be a screen full. This was the screen that was invented for, a VT100. 24 lines by 72 columns. Anybody know why it was 72? Hollerith card had 80, but the last 8 were for sequence numbers, so nobody ever used more than 72, and that's why this screen had 72 wide. Of course, we don't care about that anymore, so I'll get this off the screen. If we followed the rule that a function should exist on a screen, then nowadays, you could crank the font size down and get 200 lines on that screen. Right? Laptops nowadays with retina displays, and you could get lots of code on that screen. I don't want 20, I don't want 200. I want a different rule. The rule I want is that a function should do one thing. City slickers, right? Curly, one thing. A function should do one thing. Now, what does it mean for a function to do one thing? This is a very old rule. The rule goes back into the 1960s. Jordan and Constantine and DeMarco used to tell us stuff like this. But what does it mean? In my early days, I was famous for writing a function that was 3,000 lines of C. It was called GI. That was the name of the function, GI. Stood for Graphic Interpreter. And people might have come to me back in those days in the 80s and said to me, you know, Bob, this function does more than one thing. And I would have said, no, it interprets graphics. What does one thing mean? What does it mean to do one thing? And I think I know the answer to this question. I think I have an objective definition, not a subjective definition of one thing. What IDE do you guys use? I know that was a trick question. Yeah. VI? Not even Vim, right? Oh, you know, like and VI are not words that I associate. I used VI for 20 years, 30 years ago. Right? I'm not interested in using VI anymore. I could hardly wait to get away from VI. I was an old Emacs dude. I learned Emacs, and I became, you know, Emacs God. And then in the 2000s, along come these things called IDEs, and I switched, and now I'm an IDE guy. Lately, I have been tempted to go back to Emacs because Emacs has gotten to the point where it, in some cases, is better than the IDEs, but there's an interesting race going on. So, VI? What else? What? ED? So, I don't know if you've seen some of what these IDEs can do, but I'm going to show you something here. I've got a little bit of code on the screen. This is Java code. And I'm going to take these 2 lines right here. Now, what do these 2 lines do in this function? Well, they initialize some variables. So I think what I better do is make those 2 variables fields of the class. So I'm just going to turn those into fields initialized in the current method. Yes, that's fine. Do that. That's good. Now I'm going to take these 2 lines, and I'm going to extract them out into a function named initialize. And notice that it has replaced the 2 lines with a function named initialize, and it has taken those 2 lines and put them into a function named initialize. Now, if you've never seen anything like this, this is the state of the art of modern IDEs. Modern IDEs allow you to manipulate the code at a very high level. So you can select a bunch of code with your mouse and then say, I don't want that to be in this function. I want it to be a function on its own. This is called extract function or extract method. It will take that code out. It will put it in a brand new function. If there are any arguments that need to be passed in, it will figure out what arguments need to be passed in, and it will pass them in. If there's any return values that need to come back out, it will figure that out for you and set a variable in the call that gathers the return variable. It's very, very intelligent. Of course, it's all mechanical. Very, very intelligent. Allows you to manipulate the code at an extremely high level. And the operation I just showed you is called extract function. How do I know that it worked? Well, it turns out that I've got some unit tests here. You see that little green thing down at the bottom? That tells me that every test just passed. And I happen to know that these tests cover every line of code here. So I have extremely high confidence that the change I just made hasn't broken anything. Now I can continue this process. I can say, well, heavens, I don't think I like that. First of all, I don't like the name of that variable. Terrible name for a variable, so I think I will change the name of that variable to statement. And the IDE is smart enough to know what a variable is and how to change its name. This is not a simple text replace. Right? This is a semantic change of the name of the variable. I'm going to take this right here. I'm going to turn that into a function named makeHeader. And you can see it turned it into a function easily enough. And down here there is this function called makeHeader, which has that code. And my tests will still pass, of course, so that's nice. Heavens, what have I got here? I've got this whole while loop. That's a terrible while loop. And got gunk inside here. Oh, look at this switch statement. Let me see that switch statement. What does it do? Well, the comment tells me what it does. It says it determines the amount for each line. I hate comments that tell me what the next batch of code does, because they're completely wasted. I'm going to take that switch statement out. I'm going to turn that into a function named determine amount. Yep, and now I can get rid of the comment. And I believe that will still work. This is the process of extracting functions from inside of other functions. It is one of the tools in a suite of tools called refactorings. And if you have these tools, you can do them manually or you can do them automatically. Nowadays we have this nice little refactor menu in most of our IDEs that give us a rather large repertoire of such tools for manipulating code at a very high level. I want to focus specifically on extract function or extract method. Because how do you define one thing? A function is supposed to do one thing. How do you define one thing? If it is possible to extract one function from another, the original function did more than one thing. That's a definition. If it's possible to do an extraction, then clearly there must have been more than one thing going on. And that leads to a practice which I call extract till you drop. The way I write code nowadays is I will write it the rude way, because that's the only way to write code, is the rude way. Right? You have to think it through, and so you're going up and down the abstraction hierarchy, and you leave this massive rude mess behind once you get the code to work. And then I go through the process of cleaning the code. Cleaning can only be done after you've got it working. You cannot write clean code. No one is that good. Everybody writes crap code. And then you clean it. And the way I clean it, one of the tools I use, is extract till you drop. If I do that with that original code that I showed you, then it's going to look like that. That's the final result of that original 3 pages that I showed you before. And it's pretty easy to understand if it's a test page, include the setups and teardowns, and render it in HTML. It's a 30-second operation to understand what this function does. And if that's all you needed to know, you can walk away. If you want to know more, well, then you dive down into that function. And that function is another 4 lines, which tells you, well, you better include the setups, you better include the page, you better include the teardowns. And if you want to know what those things do, well, you can dive down a little deeper. This is polite. It takes no effort to understand this. And if that's all you needed to understand, you're done. If you practice extract till you drop, if that is a discipline that you add to your professional toolkit, you will produce lots and lots and lots of functions. And those functions will all be on the order of 4 lines long. And at this point, many of you are going, the man is insane. If I did that, I would drown in a sea of little tiny functions. I'd have no clue where any of these functions were. No, this is not correct. You will, in fact, know where these functions are. You will not be hiding the high-level structure of the system. You will, in fact, be exposing the high-level structure of the system because the high-level function will have nothing in it but high-level code. You will know where all these functions are because you will have arranged them nicely in your source files. They will all have nice names. Thing about extracting functions is you have to invent names for them. And those names tend to get longer and longer and longer the more detailed those functions get. As you are extracting, initially the functions you extract have fairly short names because they're still relatively general. But then as you extract more and more and more, those functions get really, really precise. They can only be called from one place. They are so precise. They can't be called from any other than one place, and they have long sentence-like names. And those nice long sentence-like names fit inside the parentheses of your if statements and fit within the bodies of your if statements and your while loops to make your code read with a sentence-like structure. So all of a sudden you have code that reads like that. If is test page includes setup and teardown pages, rather than a mass of if statements and null checks and dots. You have code that reads well. This code is polite. I would advise you to practice this discipline at home. Don't do it at work. No new discipline should be practiced at work because there's too much risk. But we're all programmers, right? And what do we do after we're done at work? We go home and we write more code. Because we love writing code. That's what programmers do. That's what professionals do. Professionals spend time outside of work improving themselves. You kind of hope if you go to a doctor, that doctor doesn't put in 8 hours a day at the office and then go home, put his feet up and drink beer. You kind of hope that doctor's at home cracking the medical journals. You kind of hope if you hire a lawyer, that lawyer isn't in the office 8 hours and then go home and play Minecraft all night long. Do lawyers play Minecraft? I don't know. Anyway. Professionals put time in at home. It's just what we do. And this is a perfect time to go home, spend an hour on a weekend or something, and just try a new discipline. Get good at the discipline, then bring it to work. Don't do it at work. Don't learn it at work. Learning it at work is risky, and because of the risk, you will abandon too early. You will not explore the risk properly. Do it at home. Get good at it, and then bring it to work, and you will find, if you do that you will be writing lots of little tiny functions from now on. It is a far better way to write code. If your functions are 4 lines long, how much indenting is there going to be? Not much. 1 level of indent is probably about it. Every once in a while you'll get to 2 levels of indent, but it's really hard. And if your functions are 4 lines long, and 4 lines is not the limit, it's just the extraction. If you have maximally extracted everything, then what will the body of an if statement be? 1 line, a function call. The predicate of an if statement will be a function call. The predicate of a while statement or a for statement will be a function call. The else clause of an if statement will be a function call. They will all be function calls with nice names that read like sentences, that are polite. And every function will have 1 level of abstraction, 1 below its name, and you will have this lovely tree of functions expanding downwards into a hierarchy. Most of you still think that's nuts, which is fine. Try it at home. Get used to the idea. You will find that the code is much easier to read, much easier to change, much easier to understand, and is much more polite. And other programmers will thank you for making the code much easier to approach. I think it was Jerry Weinberg, if I remember correctly. Oh, my stopwatch is still running. Stop. I think it was Jerry Weinberg who once said that software is the most complex things that human beings have ever attempted. I think this may be correct. And what convinces me of this is a simple thought experiment. I'm looking for tie shoes. You've got tie shoes. Yeah. How long does it take you to tie your shoes? 5 seconds. So you went on YouTube and you saw that one where the guy can do it really fast.
No, I've been doing it for many, many years.
Oh, all right. So just the old way your mom taught you, and crossover knot, loop it around. How long would it take you to write down the instructions so that a robot could tie your shoes in 5 seconds? This is the problem that we face as software developers. We can visualize the problem. And the problem is this fundamentally simple problem: tie your shoes. But we have to break it down into steps that are impossibly small. That's our job. And that takes a long time, and it's very difficult. The next time you're asked to estimate how long something's going to take, keep that one in mind. Don't look at the task itself, because the task itself might be simple. Look at the cost of writing down the instructions, and that's what we really have to do. One of the techniques that I use when I'm teaching is I will ask people to solve a very simple problem, which is called the word wrap problem. The word wrap problem is take a sentence that has no line breaks in it and wrap it onto a page that has a fixed width. And do that by looking for spaces and then breaking its spaces. But if you've got a word that is longer than the column, then you have to break the word. This is a pretty simple algorithm. If I were to give you 1,000 words and ask you to do it manually, you could do it in a matter of a couple of minutes. You just sit there and note where all the breaks would be. You'd be counting characters and go, okay, there. You could do it in a couple of minutes. How long will it take you to write that code? Now we got everybody doing the estimation game, right? How long would it take me to write that code? Huh? How long will it take you to write that code? Do this as an experiment one day. Just think about it, write it down, how long you think it's going to take you, and then notice that it takes you 3 times longer than that. This is a fundamental truth of software. Everything takes 3 times longer than you think it will, even when you know this and take it into account. You had a question? Of course your test cases are included. But if you write test cases, that should shorten your time. Right? If you write test cases, if you follow the practice of testing, that should make the whole process shorter, not longer, because you will spend no time debugging. And how much time does debugging take? I don't know. It depends on if there's any bugs. Well, if you follow the testing discipline, there will be no bugs, at least no obvious bugs. Most of the bugs will be gone. And so that should shorten your time. It's one of the reasons that people get caught in this trap. They think, okay, I'm going to estimate this now. Does that include my test cases? Well, if not, then you'd have to grow your estimate. So of course it includes your test cases. This is, again, part of this professionalism discipline. It's always shorter to include your test cases. Yep. Indenting, I've talked about that. I talked about one thing. Everything's at the same level. Good. Does anybody, 2 paragraphs. I actually talked about that. Good. Talked about names. Good. How long should the name of a variable be? How many characters should be in a variable name?
As many as it takes.
Okay, as many as it takes and no more. Okay. 50 is good, yeah.
As many as it takes to describe
So can I erase this? Raffle tickets at registration. Can I erase that? Good. I wish that chalkboards were still the rule because they work. Whiteboards are the invention of Satan. Oh, the markers are. Well, and the boards too. Have you ever, erased something on a whiteboard? It won't erase. It won't. Never mind. All right. So, for int. See if I can actually use this whiteboard. It's been so long. Int I equals 0, I less than 20, I plus plus. Is I a good name for that variable? Well, it describes nothing.
Well, if you've got a single function, if a single behavior that you're implementing, and you're iterating across a set, then it's very clear what it does.
You're exactly right. I don't need the name to describe anything because, well, I left something out. It's very clear what that variable does. I don't need a descriptive name for it. In fact, if I were to lengthen that name, you would get mad at me. If I named it index, you'd go, well, what'd you do that for? It should be I. And this leads us to a fundamental rule for variable names. The length of a variable name should be proportional to the scope in which that variable is active. This variable is active for 1 line. 2 lines if you count the for statement. But the scope here is just the body of the for loop. And the body of the for loop is very small, so a single character variable is perfectly fine. If that for loop were larger, 10 lines, then you might think to open up that variable name and give it a slightly longer name. If the variable was a local variable of a function, which spanned 20 lines, because you don't follow my rule of extracting, then probably you need an even longer name. If you're writing in C++ and the variable is a member variable, well, then you probably need a longer name. If you've got a global, and we do have globals, then you need a very long name. The length of a variable's name is proportional to the size of the scope in which it is active. This is the best rule that I've been able to come up with. What is the rule for a function? How long should a function's name be? And remarkably, the rule is exactly the opposite. The larger the scope of the function, the shorter we want that name. Because a function with a very large scope must be very general. And so we don't want to have it a nice, long, specific name. We want a short name. So, for example, consider the name open for opening a file. It would be very unfortunate if this function were named open file and throw exception if not found. We wouldn't want to call it very often. In fact, we'd write another function called open that would call that one. We want functions at a high level, broad scope, to have very short names. But as we get down lower in the scope hierarchy, the names get longer and longer. So member function names get a little bit longer. Private function names get a little bit longer. And then as you extract and extract and extract, those names get longer and longer and longer as their scope gets smaller and smaller and smaller. What about class names, module names? They follow the same rule as functions. High-level modules, really short names. Low-level modules, really long names. Classes follow the same rule. Those are the rules that I use anyway for variable names. Other than that, I want them to be descriptive. There are tons of rules about how to make them descriptive that I'm not going to go over with you. How many arguments should a function have?
You say no more than
Yeah, no more than 3, yeah. This is a rule that I put in place a long time ago for myself, and I use the following reasoning. The easiest function call to understand is one that has no arguments. It just reduces all the degrees of freedom down to 0. 1 argument is not hard to understand. 2 arguments create a lot of possible variability, but one of the things that's not hard to understand about two arguments is their order. Human brains can keep two things in order pretty easily. How many possible orderings are there for two things? Two, yeah, we can do that, humans. Three arguments, well, we can do that. We can keep them in order, sorta. How many possible orderings are there for three things? 6. Yeah, it's the factorial problem, right? Okay, so I'll tolerate 3. 4, how many possible orderings are there for 4 things? 24. Yeah, it's a little hard to pull that out. I don't want to even go there, unless, of course, I have 4 arguments that can be grouped into 2 and 2, sort of like a rectangle, top left and width and bottom right and height, something like that. Then I can keep them in mind. But usually I don't want 4 arguments, and certainly not 5 and 6 and 7 and 8. That's just rude. So it's polite to your reader to keep your argument strings as short as possible. There's another argument here, which is if you've got 4 or 5 or 6 things that are so cohesive they're being passed into a function as a unit, they probably ought to be, if you're writing in C++, some kind of object. If you're writing in C, some kind of data structure, some kind of struct. You probably ought to have done that work yourself. So another reason to keep your argument lists small. I specifically don't like output arguments. Arguments whose job is to catch a return value. I don't like those. I would rather the return value come out of the function rather than being caught by an argument. And I know there's all kinds of issues with this, especially in C. Do you guys have error codes returned by your functions? Do you have a hopefully not.
Just like exceptions. I don't think he ever throws an exception.
Well, in C++ you can throw an exception.
I mean, think about what that does, right? You're somewhere deep in the code, something that can go wrong, and making sure that it's actually being handled at the scope where there's some visibility is a tough thing. And exceptions just allow you to blow that off, and so you're just littering your state space with unknown state transitions. You have no idea, and changes also ripple globally. So return values and exceptions are the 2 blackest evils I've ever seen in software.
We can have that debate. I'm not going to go down the rat hole with you just at the moment, because I want to come back to the return value issue. Anybody have a file named error.h where all the error codes are defined? What happens if someone adds a new error code? You have to recompile the world. Everything has to recompile because everybody includes the error code. So you don't add a new error code, do you? Because that's expensive. You get creative about the meanings of older error codes. Well, that could mean this, right? Or if you're absolutely forced to add a new error code, do you touch all the .o files so that you don't recompile the world? We found everybody who did that and shot them long ago. This leads to a point, and the point is that there are certain files in our systems. Error.h is one of them, but it's not the only one, which are dependency magnets. Everybody depends on them. And those make the system rigid. We try not to create files like that. We don't want these massive files that everybody includes or everybody depends upon, because to change them causes this massive ripple throughout the whole code. Remember my EEPROM story, right? We couldn't have any of those global modules that if you made a change would force all of those chips to change. We needed the independent deployability of those chips. We need to be able to compile each chip as an independent unit and ship it as an independent unit. So we had to abandon any concept of these global files that everybody include. Most of us should be following the same kind of rule. I presume that you have the issue where big changes are bad and small changes are good. I don't like flag arguments, Boolean arguments. If you have a Boolean, if you're passing a Boolean into a function, what you've really done is you've hidden the fact that there are two functions. There's probably an if statement in that function that you're passing the Boolean into, and that if statement does two different things depending on the state of the Boolean. Well, you should probably have two different functions rather than passing in a Boolean. Besides that, nobody understands what that false means in the function call. Anybody read one of those? It's a function call and it's got a couple of arguments and then there's this false. And you think, well, what the hell's that? And then your next thought is, well, the author knew what it was. I don't have to bother with it. Right? Try not to put Booleans in your argument list. They're just a bad habit to get into. Running out of time for this. How much time? In fact, we got about 2 minutes, don't we? So, because we have 2 minutes, are there any questions? Yeah.
So, given that a lot of people here work on embedded systems,
Yes.
Doing the code,
Extract till you drop.
Extract, we go, oh my God, the stack.
Yes. Oh my God, the stack. Yeah.
And knowing that there's inlining, but inlining is, I'm curious if you see any development in improving the inlining.
Oh, some of the C++ compilers are pretty good at inlining, right? But you're right, the stack is an issue. So if you've got some kind of a process and you've got a limited amount of stack space, then deeply calling lots and lots of functions suddenly becomes an engineering trade-off. I don't want to blow the stack so much. Now, the other trade-off is real time, right? Because it takes time to call those functions. You've got to create the stack frame. So there's microseconds involved if you're running in low clock rate mode. So if you...
It's the variableness of timing.
Yes.
It's not the time it introduces.
Well, it can be the absolute amount of time as well, but the variable is...
And
Yeah.
maybe you page some things out on a function call.
Yep.
That's the point.
Mhm.
That's why it doesn't work in real time.
So in those cases, you're probably going to have to pop the bubbles and grow the functions again. Some of them. Right? But you can trade off your rudeness against engineering necessities. You don't need to follow the opposite rule, which is all functions must be big because we've got stack limitations. Second thing on stack limitations. Do any of you follow the actor model? Or the Erlang kind of model, where you are not allowed to block a process. A process can run, but it must never wait. The only way to allow a process to wait is to terminate the process, to start a new process that checks the event, and then when the event occurs, it starts yet another process. It's the actor model. And in a model like that, there is only one stack in the system. You don't have to allocate stacks for all the processes. So this is the kind of model that old telecom switches used to use, because they'd have to have thousands of threads running. And there was no way to allocate enough stacks for thousands of threads. So they'd use an actor model. There was one stack in the system, and they could keep control over their stack usage pretty easily. It was a stack problem, in case you didn't know this, that caused the Toyota cars to run out of control and kill a bunch of people. They blew a stack, corrupted some of the memory in the process that controlled both the accelerator and the brake. Note to future self, do not put the accelerator and the brake in the same process. And people would run off and smack into trees. So it's an interesting issue. Thank you for that one. And I think that's probably all we have time for, so thank you all for your attention.